Okay, so this video is to cover enzyme kinetics and to help prepare you for the work you're going to be doing in lab characterizing an enzyme. So first let's talk about what enzyme kinetics is. Okay, so there are only certain things that we can measure in the lab, and we don't yet have the ability to look at individual molecules, with our eyes and zoom in and see exactly what they're doing. So we have to have some kind of combination if we want to figure out what's going on with the molecules and how enzymes actually make reactions proceed faster. We have to have some way to connect the things we can measure in the lab with a conceptual picture of what molecules are doing. Okay, so we're going to be combining, again, all of our measurement techniques with our understanding of functional groups and basic organic reaction mechanisms to try to understand how enzymes are working, and the connection between these is going to be a mathematical model that connects our data to a conceptual picture. Okay, and we call this enzyme kinetics because we are following the change in either reactant concentration or product concentration, usually as a function of time, and it's a dynamic thing. So the model that we're going to use both in lab and in talking about enzyme kinetics is called the Michaelis-Menten model. And the reason we're using the Michaelis-Menten model is because it is the simplest that we have in terms of the number of moving parts, the mathematics, for basic enzyme reactions. Okay, so not all enzymes follow this particular conceptual model because they maybe have different numbers of moving parts or cooperativity of some sort. Okay, but the general principles, of Michaelis-Menten kinetics apply to many, many enzymes, and they can give us an understanding for how we can figure out the reaction mechanisms, the catalytic mechanisms that we talk about in other lectures in this class from things we can measure in the lab. Okay, so enzyme kinetics is the quantitative study of the rate of chemical reactions, and we're studying enzyme catalyzed reactions, but reactions, again, in general, can be studied kinetically in chemistry. Again, my key focus on this is that it connects what we can measure, with a molecular view of the reaction, what is going on in the reaction, and so we're going to be able to relate reaction rates to free energy and to equilibrium. And we're going to use terms like velocity. Okay, so if you study physics, you know that velocities have both a speed and a direction. Okay, so when we talk about a velocity in an enzyme catalyzed reaction, we're talking about the rate, and the direction. In this case, the direction is product formation. So when we talk velocity, we're thinking about how fast our reactant is moving towards becoming product. Remember that we call our reactants the substrates. So we're going to be measuring velocities. This is one thing we can manipulate in the lab. We can change this. So we can manipulate this in the lab. And so that's one of the things that we can control. Remember from Gen Chem that little k, is a rate constant. So when we talk about enzyme kinetics, we're going to be talking about lowercase k that's going to be a rate constant. Anytime you see a lowercase k, whether it has a, no matter what the subscript is, okay? And then uppercase k's, remember that those are equilibrium constants, usually. Okay? So they have fundamentally different meanings, okay? And we're going to see both of those in our Michaelis-Menten model for our kinetics, okay? So in the simplest sense, okay, the simplest rate equation, so this is a rate equation, right? This is a basic rate equation. And in the simplest case of a rate equation for a first order reaction, okay, so this is a first order reaction, right? Because, again, remembering our kinetics from general chemistry, because the exponent, okay, on our, I'm looking for my, there it is, okay. The exponent on our substrate concentration, our reactant concentration is a 1. Okay, so this is a first order reaction with respect to the substrate concentration. And K is our rate constant. Okay, so as we go into the Michaelis-Menten equation, or the Michaelis-Menten kinetics, the reason I want to actually derive the equation is because, especially for you biologists in the class, you may never, this may be the only time you see the mathematics derived between our conceptual picture and, again, the data we can collect in the lab. And it's kind of nice and clear, and it really connects our understanding of things like substrate affinity or ability to turn the reactants into products. So that's why we're going to go through the mathematics. But then at the end of it, okay, the important thing is going to be what each component of our equation means, okay, and the conceptual picture, okay, which you're going to see this figure right here many times over, and this is the conceptual picture that I'm talking about, okay. So what do we have? So we've got our enzyme molecule, okay, and our concept of how enzyme catalysis works is that the enzyme has to bind to the reactant or the substrate. And so when you have the enzyme and the substrate binding via non-covalent interactions, you have what we call the enzyme substrate complex, or the ES complex. And then that is going to decompose, if you will, to enzyme and product, and the product actually winds up getting released. Okay, so we have two processes. We have the process of enzyme binding to substrate, so and that is because it's dictated or it's governed by non-covalent interactions. Okay, this is a reversible product. The substrate can diffuse out of the complex. Okay, so this is an equilibrium process, right, where you have binding or you can have dissociation, right? So we have two processes. And so what we do is we call the rate constant for binding K1, and the rate constant that guides dissociation, K minus 1. Okay? And then our enzyme substrate complex, okay, is going to break apart once the substrate has been converted to product. Okay? So that is governed by the rate constant K2, okay? And you will notice, okay, that in this view, okay, there is no reverse reaction, K minus 2. I'm going to put it here. But what we'll find out as we derive the equation is that we don't show K minus 2 because one of the assumptions that we make, okay, when we derive the Michaelis-Menten equation is that for all practical purposes, this reverse thing doesn't happen. You don't get product combining with enzyme to then, reverse the chemical reaction and make an enzyme substrate complex. Okay, so this is a spoiler alert, okay? We're going to assume this doesn't happen. Or better to say that it's negligible. Okay, so that's setting the scene. Okay, so our enzyme and our substrate have to come into physical contact in order for the enzyme to help the reaction of turning substrate into product. All right. So I'm not going to show you the animation, but you can, the animation or a link to the animation is posted on Brightspace for you, okay? And it shows the process of binding to substrate and product release. Okay. All right, so the Michaelis-Menten equation, or the derivation of the Michaelis-Menten equation, okay, starts from, again, our beginning point, which is a conceptual model, right? So we're assuming that if our molecules follow this picture, okay, K1, K minus 1, and this is K2. Okay, and so these are little k's. I'll make my little k's with kind of a curly top to distinguish them from capital K's. All right. All right, so that's our conceptual picture. And in order to process the mathematics for it, what we're going to be doing, okay, is we are going to be writing rate equations, okay, like this rate equation you see here, okay, and we're going to be defining constants that have physical connections to the different parts of this process, okay? All right, so the first thing we're going to do is we're going to state the assumptions, and then we're going to go through the derivation. Okay? So first assumption, okay, and I will, this is one of our learning outcomes or learning goals for the study of enzyme kinetics, is for you to understand and know what these assumptions are. So this is super important, okay? All right, so assumption number 1, okay, has to do with the conditions under which we do our experiment, okay? So I guess one thing we'll start with, okay, is when we use the Michaelis-Menten model to analyze our data, we have to do our experiment in such a way that these assumptions are true, okay? Because the assumptions are going to let us kind of ignore things and get rid of some of the mathematical complexity, okay? So we set up our experimental conditions. So these are true. And then, and then thing number 2 is that the assumptions eliminate some mathematical terms. Let's just put it that way, okay? So they simplify the model. All right, so assumption number 1, okay? Assumption number 1 has to do with what we measure, okay? So what we're measuring, okay, is we're going to look at initial rates, okay? So what that means, okay, is we are going to look at product formation. So this is the very first assumption that I told you about, is that we are ignoring k to the minus 2, okay? So we're assuming that the thing we measure is how much product is being made, okay? And, you know, not giving it time to recombine, okay? So, because if you kind of let your system evolve long enough and get to equilibrium, eventually you might get some, you know, product recombining with the enzyme. But we're saying we're going to do our experiment where we're only looking right away at product being formed, okay? All right, so the second assumption we're going to make, okay, is that the binding and dissociation of the enzyme and substrate is at equilibrium. Okay, so what that means, okay, is that these rates right here, for the forward and backward, the association and dissociation, okay, are going to have hit their equilibrium point. So what that means, okay, I'm gonna show you on the next slide after we talk about assumption number 3. Okay. All right. So the third assumption, okay, is that we use an excess of substrate. Whoops. Okay, so this is what excess of substrate used. Okay, and whoops. We're going to call this the steady state, okay? So assumptions number 2 and 3, where we use an excess of substrate so that we can do what's called the steady state approximation. So let's leave this slide for a minute and go to the next slide, just so that you can see, like, physically what I mean by these assumptions, okay? So if we're looking at, let's say, the amount of substrate, the amount of product, and the amount of enzyme-substrate complex. So we've got substrate, product, enzyme-substrate complex, and free enzyme, okay? And so at the very beginning of my experiment, the instant things are mixed, I have free substrate and free enzyme, right? So this little first yellow region here, okay, is called pre-steady state, okay? So what's happening under this is that the substrate and the enzyme are diffusing and finding one another initially, okay? And then, okay, so then we get enzyme-substrate complex. Now, if you look in this, what I said was the steady state approximation, these steady state conditions, okay, what we're assuming, okay, is that the amount of free enzyme has hit a point where it's not going to change, and the enzyme substrate complex, okay, stays relatively constant, because as soon as product is released, another enzyme molecule can pick up another substrate molecule, because there's so much substrate around at this point in time. Okay. So if we look, okay, you know, we have a ton of substrate, all right, when we're at our steady state conditions. If this is concentration, right, I start with a really high concentration of substrate. Notice that my concentration of enzyme is very low, okay? So when my substrate concentration gets to the same point as the enzyme concentration, that's when, you know, as I make product, I will be running out of substrate, okay? When I'm in this region here, I've always got substrate molecules for the enzyme to find, okay? So what this means is the amount of enzyme substrate complex that I have, okay, when I am in the steady state region, okay, is going to be dictated by what? By the affinity the enzyme has for the substrate. Okay? So it's going to be, so when I am in like this zone, okay, the thing that controls how much of this is there, how much of that enzyme substrate complex is there, is not whether the enzyme can find the substrate. There's lots of substrate around, it can find it. It's just dictated by the affinity of the enzyme for the substrate. Okay, so when I do my experiment, when I'm only collecting data in this region, okay, so I don't want to go too late in my experiment. I don't want to look too early, okay? I want to be in this zone when the steady state applies, because then I'm going to be able to learn things about the affinity my enzyme has for its substrate. And that's really important to me, okay? Well, it's a really important thing to understand. All right, so our assumptions 2 and 3, again, get us to that steady state condition, okay? Assumption number 2 is that we're gonna collect data during the steady state. And assumption number 3 is really, we're gonna provide it with enough substrate that assumption number 2 works, okay? All right, so the next assumption, okay, is we're gonna do something called measuring the initial velocity of the reaction, okay? And I am going to give that an abbreviation called V sub 0, capital V sub 0. This is the initial velocity. Okay. So when I do my mathematics, and I am talking about the reaction rate, okay, in Gen Chem you called it rate, right? In biochemistry, we're going to be calling it V0. That's the thing we're going to be measuring. It's the thing that we are going to be writing our rate equations. We're going to use that for our rate. All right. And then the last assumption is just that our enzyme can exist in 2 states, as free enzyme or as enzyme substrate complex. This is free enzyme, and this is enzyme substrate complex. So the total amount of enzyme present at any time, we would write as E in square brackets with subscript of total, and it is going to be the sum of any free enzyme and any enzyme that is in the enzyme substrate complex. Okay? So that is, this is, stating our conceptual picture, okay? This is turning that conceptual picture into an equation that's going to be used, okay, in our derivation, all right? All right, so let's get to our derivation, okay? All right. So again, we are going to be deriving the Michaelis-Menten equation using these assumptions. We're by applying these assumptions. All right, so this is E plus S, K1, K minus 1, ES, K2. I'm initially leaving K minus 2 in there, as we derive, we'll see it disappear, okay? All right, so the first thing we're going to do, okay, is we're going to write an expression for the rate of enzyme substrate formation, okay? And so how can we get the enzyme substrate complex? We can come to it from this direction or from this direction, okay? So if we write our rate equation, we've got, K1 time, missed a bracket there, times the 2 things that it's going to depend on, right? And then the other way we can make this is by breakdown of, recombining of product. So K minus 2 times E times P. All right, so now what we're going to do is we're going to apply assumption number 1. Assumption number 1, which means we can ignore this or neglect this, let's say. I like neglect better than ignore. Okay, and so that gets us to the rate of enzyme substrate formation is equal to just K1 times the concentrations of the enzyme and the substrate. All right. So remember the relationship that we wrote over here with assumption number 5? So I'm going to, let's see if I can copy this and save us some. Copy this. All right. I'm going to shrink it a little bit. There we go. So assumption number 5 told us our, whoops, did I do the right one? Yes, I just wrote it a little differently. Okay. So the total amount of enzyme is a combination of free and enzyme substrate complex, right? So I can, so then I can plug that in here, okay? So I get the rate of enzyme substrate formation is K1 times, let's see, I'm going to, let's see, how am I going to write this? So this is free enzyme here, right? Because I'm making ES formation, so I'm going to rearrange for free enzyme. Okay, so it winds up being enzyme, the total amount of enzyme minus enzyme in the enzyme substrate complex. Okay. All right. So that makes this E free, oops, sorry, E total minus E in the enzyme substrate complex. And this whole thing, again, is going to be multiplied by substrate concentration. Okay. All right. So we've got an expression for the rate of the enzyme substrate formation. Okay. Now, the next thing we want to consider the breakdown, okay, of the enzyme substrate complex, or the formation of product. Okay, so now we want to know, how do we get here? Okay, because we know that to go from here to get to here, we have to go through this enzyme substrate complex. So first we worried about how it was formed. Now we're going to switch. Let's see, what color should we do? Let's go purple. And we're going to talk about the rate of enzyme substrate breakdown. Okay? So, because we have those two things happening. Okay? All right, so the rate of enzyme substrate breakdown is going to be a combination of both dissociation, okay, dissociation, or being converted to product, okay? So we're going to have dissociation is our K minus 1, and that's times our enzyme substrate complex, which we are writing as E subscript ES. All right, plus the second way it can decompose is into product formation, okay? So that is going to be our K2 times that, all right? So we're going to simplify this, right? So rate of ES breakdown, because we can combine terms, right? We've got the same term here. So we've got K to the minus 1 plus K to the minus 2, and we're just taking enzyme substrate complex out of that. All right. So now here we get to apply another one of our assumptions. Okay. So we're going to apply assumption number 2, okay, which is saying that the rate of formation equals the rate of breakdown. Okay? And that is how we are going to combine these two things. Okay? So let's go back. What was assumption number 2? It's that we're at the steady state. And again, the reason that we can do this is because we're going to do our experiment where that is true. Okay? Now, why are we bothering? Where we are going with this is we are going to be we're deriving an equation, okay, that is going to be able to reproduce the shape of our data points and allow us to connect that data to several meaningful things, one of which deals with affinity and the other of which deals with chemical catalysis ability. Okay. All right. So I'm going to cheat. Okay. So oops. All right. So we already wrote that rate of formation equals rate of breakdown. So this is equal to this. So I'm going to take this part and this part, and I'm going to combine them into an equation. Okay, so we've got this right here, K1, and that's E total, oops, minus E in the enzyme substrate complex times substrate is equal to K to the minus 1 plus K to the 2, sorry, times E ES. All right. Okay. So now what we're going to do is if we start with this, okay, and we're going to rearrange it to put all the rate constants together. Okay, so I'm gonna, let's see, let's just find a black, there we go. Okay, so the next thing that happens is we're gonna rearrange to put in terms of rate constants. All right, and so again, that's just some algebra. That is some algebra that we're not going to go through every step of, but I'm going to make sure that I have enough pages here to finish this. There we go. All right, so when we rearrange that, okay, what we get, okay, is we get K to the minus 1 plus K2 over K1, right, and then the other side of the equation, okay, winds up being our total enzyme concentration times the substrate concentration divided by, okay, the enzyme in the enzyme substrate complex minus the substrate concentration. So I'm going to just neaten up my, all right. So that's what we get when we rearrange it, okay? All right, so what we're going to do now is so our next step is going to be to define a new constant, okay? Define a new constant called K, capital K, okay, sub M, the Michaelis constant, okay? And I'm gonna use that part of my equation. I'm just gonna call it Km. All right? And if we think about what it means, right? So this is our K1, this is our K minus 1, this is our K2, okay? And so those rate constants define, okay, whether the enzyme substrate complex is formed or breaks down. They control formation of the enzyme substrate complex, right? All right, so the kind of this important feature, okay, of this constant, okay, is that it tells us about affinity for our substrate, okay? So this is, so Km, Km tells us about enzymes affinity for substrate, okay? All right, so now we have a new constant, right? And so we can write our equation in terms of that. We can say Km is equal to, and for the purposes of being speedy, I'm going to put that on the other side and make it all the same color. Okay, so now we have the equation in terms of our new constant Km. Okay, so the next kind of steps that we're going to take, okay, is so we want to have this again in terms of either data that we can measure, things that we can control, okay, or parameters that we can fit our data to, okay? So, spoiler alert number 1, so this will be a fitted parameter, okay? So we can't control Km, it's something that we're interested in learning about, affinity for substrate. So this will be a fitted parameter once we collect data, okay? So our model is gonna help us take our data and figure out what this Km is, okay? So that's thing number 1. Now let's look at what else we have here, okay? What do we have in our equation? Well, we have substrate concentration. We can control that, right? If we're mixing things up in the lab, we can control substrate concentration. We can control total amount of enzyme, right? Because we know how much enzyme we're going to put in, okay? What we don't know, all right, is, we don't know this, enzyme substrate complex thing, right? And so, again, our next goal is to kind of get rid of this enzyme substrate complex term and put it in terms of things we can measure in the lab. Okay, so how we're going to do that is we're going to, 1, solve for RES term. Okay, and then the second thing we're going to do, okay, is we're going to define the reaction velocity that we can measure. Okay. In the lab, and use it to help get rid of our enzyme substrate term. Okay? So that's where we're going. Okay? All right. So solving for the ES term, and so that's not going to show that algebra. That's rearranging this. So it's E sub ES equals, and that's going to be enzyme total times the substrate concentration divided by Km plus the substrate concentration. Okay, so we'll put that on the next slide. And then we're defining our reaction velocity, okay, which is just a regular rate equation if we consider it in terms of enzyme substrate complex, right? So that would be a velocity is equal to the reactant, right? Our enzyme substrate complex times K2, right? That controls product formation, okay? All right, so, oops. I guess I'll write this up here. All right, so we got enzyme substrate is total times S over Km plus S. All right, so this should be starting to look a little familiar to you if you've seen the Michaelis-Menten equation before. All right, what we're going to do, okay, is we're going to take this equation right here, and we're going to multiply both sides by K2, okay, and maybe we will see something that looks like this, and we can substitute V in for that, because V is something we can measure in the lab. Aren't we crafty ones? All right, so our next step is to take, let's see, and I'm going to call this equation star, okay, and multiply both sides, so we're not changing anything, by K2, okay, and what do we get? We get K2 times equals K2 times our total enzyme times substrate concentration, Km, plus substrate concentration. All right, and if we look, K2 times enzyme substrate concentration is our velocity. So we're going to sub in this equation. So we're just going to sub in V. So we haven't done red yet. Okay. Sub in V. And we get V is equal to this thing that's on the right. All right. So, whoops. 2 total times substrate concentration over plus. All right. Okay, so now if we think about it, okay, let's think about when we would see the fastest rate of product formation. And I'm going to skip ahead a few slides for a second to this picture, okay? All right, so this is the fastest rate of product formation. So if every enzyme, so if we need the enzyme to see the reaction happening, right, then we're going to see product when an enzyme molecule releases a molecule of product, okay, when an enzyme releases molecule product. So what we're going to define is something called Vmax. So what that is, okay, is let's assume, okay, that each one of these cute little kittens, okay, is an enzyme molecule, okay? And what you see in the top row here, when the cat is holding the balloon, that's the enzyme substrate complex, okay? So the balloon with its full tail is the substrate. Okay, so this is the substrate, and the cat is the enzyme. Okay, and the product is going to be the released balloon that is, if you'll notice, missing part of its tail. Okay, so this is the product. Okay, and this is the enzyme. Okay, so this is enzyme, the free enzyme, and this is the product. Okay. All right. So what you'll see is the fastest or the most product you can see, okay, is if you have all of your enzyme molecules, okay, that have substrate bound at the same time. Okay, so we've got our enzyme is saturated with substrate. All the enzyme molecules that are gonna bind product, or that are going to bind substrate, have bound it. And if they all released at the same time, we would see this amount of product. So there's 6 enzyme cats, and so we can see 6 balloons with their tails cut. Okay. All right, so that's the fastest we could possibly see. Okay, so we can now make a mathematical assumption, okay, which is, okay, is that our maximum rate is going to be, okay, so I'm going to call this V maximum, is going to be when all of my enzyme is bound to substrate, all right, and so my enzyme substrate complex is equal to my total amount of enzyme there, concentration-wise. And then again, remember, K2 is the rate constant that tells us about product formation, right? All right, so now let's go back. We're almost done with the derivation, okay? So what we're gonna say, again, we're gonna define our maximum velocity as equal to K2 times the total amount of enzyme. All right? Aha! So here we go. And if you look carefully, I'm going to change to blue, you'll notice that this right here matches our Vmax, okay? So when we substitute that in, we get the Michaelis-Menten equation at long last. Okay, so this is going to be, Vmax times substrate concentration over Km plus substrate concentration. All right, so what we've done, okay, is we now have an equation, okay, with things that we can control in the lab and things that we can measure. So let's talk about what we can control and what we can measure, okay? So, substrate concentration, okay? We control this in our experiment. What do we measure? We measure a velocity. We measure product formation. And sometimes that is measured by, loss of substrate. So for example, if your reactant or your substrate is colored and the product isn't, the thing you can measure is the loss of color. Whereas, many times we arrange things so that our product is colored so that we can look at the formation of color. But there's lots of different ways of doing the measurements, but this is the thing we control over here. This is the thing we measure. And then these two things right here are our fitted parameters. Okay, so we'll talk about curve fitting in a minute. Okay, so let's pick a different color for the things that we fit. We'll do bright green. Okay, so these things right here, okay, are going to be, these are going to be derived from fitting the data to this equation. And the Km is going to tell us about the affinity for the substrate, and the Vmax is going to tell us about K2. And K2 tells us about how good the enzyme is at actually doing the chemistry that we need to do to make product. Okay. All right. So I know that was long, but it really is important to me that you see how the choices you make in the lab and the kind of conceptual picture that you have in your mind as to what the molecules are doing can be connected by the way you process your data. And the way we process our data is by fitting it to this equation that connects the conceptual picture via, assumptions that we control with our experimental setup to, what actually happens and what we can measure. Okay. All right. So, again, we've been through that. Okay, it's important that you see that journey, how we get from one thing to another. What's important in terms of takeaway messages, okay, is what these parameters mean and how measuring those and determining those parameters and tweaking either the conditions of our experiment or making mutations to our enzyme can help us figure out reaction mechanisms, which again, we're talking about in class and other lectures. All right, so for Michaelis-Menten kinetics, okay, we've got our V0, okay, so this right here, oops, I didn't mean to erase that, I meant to highlight it. So this right here, this V, okay, the velocity is what we measure, and remember that we are doing our experiment so that we're doing it only in that steady state region where we are well before running out of substrate. So this this rate we measure is V0, okay? So we're going to measure the initial velocity, okay? And then depending on depending on your affinity for your substrate, okay, and your ability to do the reaction, that V0, okay, will vary with your substrate concentration, okay? So remember that we have this maximal velocity, and we're going to see that maximal velocity when we have so much substrate around, again, that all the cats are holding their balloons, okay? All the enzymes are saturated with substrate, okay? All right. So what we do in the lab, okay, is we are going to be manipulating. I said one of the things we can control in the lab is the substrate concentration that we put into our experiment, okay? And so what we're going to be doing is we're going to be doing, we're going to be measuring the initial velocity over and over and over again at different substrate concentrations. So each one of these data points, okay, is a different experiment. This is not one experiment where we look at product formation over time, okay? This is the result of a bunch of different experiments. This is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this curve is the result of 9 experiments, where V0 was determined at different substrate concentrations, okay? All right. Okay, so let's summarize. This is our conceptual model, right? And this is our definition of Km. It relates to those rate constants that control the creation of the enzyme substrate complex, okay? And again, this is correlated with affinity for substrate, Km, affinity for substrate, okay? It is not the exact same thing as an association equilibrium constant, because the regular association constant would be, the equilibrium constant that governs this. But again, because we can get a chemical reaction happening that causes this to disappear, okay, we're not really determining the exact affinity when we determine Km, okay? So that is the caveat there, but it is highly correlated with affinity. Okay, and then our Michaelis-Menten equation relates reaction velocity, okay, and again, it's V0 because we're setting up our experiment for that to be the case, where we're only looking in that regime. And then our maximal velocity, which is related to both how much enzyme is there and how fast it can turn reaction into product, and then our Km. Okay. All right. So there's one more thing I want to say about the reaction, the Vmax. Okay. So we've already talked about the catalysis, haha, bad pun, where we have, the cat holding the balloon and the product is the balloon released with a shorter tail, okay? Now, one reason I made this figure was to emphasize that Vmax is proportional to how much enzyme is there, okay? So if I have more enzyme, I'm going to be able to see more product released in a unit of time. If I have fewer enzyme molecules there, naturally even if all of them are releasing product at the same time, I can only have less product that I see, okay? So while we measure the V0 in the lab, we control the substrate concentrations, and by doing fitting of our data to this equation, we can get Vmax and Km. Km is going to tell us about affinity for substrate. Vmax, okay, is related to how much enzyme is there and the catalytic rate constant. Okay, so Vmax is not the catalytic rate constant, but if I know how much enzyme I have, okay, I can figure out what my catalytic rate constant is, right, by taking the Vmax I measure and dividing it by how much enzyme I put into my experiment. Now with proteins, it's sometimes hard to know what your concentration is unless you have completely pure enzyme. So when you do this type of experiment in lab, we're going to be working with an extract. We're not going to be working with pure enzyme. So we will only be able to get Vmax. We won't be able to get K2, but we can make internal comparisons. So you can, compare your Vmax under, let's say, different conditions, okay, or with different with maybe different additives to your experiment, okay? Okay, so this is just an overview of what this is going to look like in the lab, okay? So when you do an individual experiment, okay, what you're going to be measuring is product concentration versus time, okay? Maybe it's in minutes, maybe it's in seconds. Okay. So if we were to look at this for, till we ran out of substrate, okay, what we would see is an increase in product, and then eventually it would start to level off as we ran out of product, okay? And so what we're interested in, again, is our V0. So that's going to be the slope of a line, okay, from this part of the curve, okay? So this slope is your V0. So what you'll do is you're going to be collecting data for some amount of time, and I'm just going to make this a little smaller so that's not so, there we go. You're going to be collecting data, and if your data winds up leveling off, okay, then you're going to truncate the data and you're only going to fit a line to here, and you're going to use the slope of that line and you're going to call that your V0. So each one of these experiments will be done at a different substrate concentration. So in this figure, I have 4 different substrate concentrations. That's the absolute minimum that you would want to do. If you notice, our Michaelis-Menten plot over here, okay, had 9 different concentrations done. So that would be 9 experiments where you fit to a line and you get V0s. Okay, so these experiments give you V0s. So we have 4 values for V0. All right. And so again, we're not going to get a very good definition of our curve with only 4 points. So again, you want to use at least twice that, right? All right, so there's 2 ways you can process this data, right? You can fit it directly to the Michaelis-Menten equation, okay? Now this equation defines this shape here, which is a rectangular parabola. It is not a trend line that you can use Excel for, okay? Nonlinear curve fitting, you can do in Excel, but it is a pain in the tuchus, I think. And there are faster and more efficient ways. So what we're going to use, we're going to use Excel to get V0s, okay? And then what we're going to do is we're going to use Mathematica to fit to the Michaelis-Menten equation. And get, whoops, not V0, Vmax and Km, okay? The other way you can do it, okay, so this way right here is going to be more accurate for the way we're doing our experiment. You're not going to have time to do, 10 replicates and have each point V0, at each substrate concentration, precisely narrowed down, okay? So the other option, the other way one can process your data is to do what's called a Lineweaver-Burke plot. So this is also called a double reciprocal plot, so AKA double reciprocal plot. Okay, so this is Michaelis-Menten, or we're going to call it a Michaelis-Menten plot, okay, because we are going to do nonlinear curve fitting. Okay. Now, the Lineweaver-Burke, if you just take, if you just take the reciprocal of 1 over V0, okay, and 1 over this side, right? So both sides. So 1 over both sides, what you get is you get this equation right here, okay? And if you'll notice, this equation is the equation for a line where, I'm gonna get rid of that, where 1 over V0 can be our y equals m. Our slope is km over V max times x, right? Which would be 1 over s plus b. All right, so what do we have? We've got our y, which is 1 over V0, that's our y, and our x is 1 over substrate concentration. So you would plot just the reciprocal of those V0 data, V0s that you measured, and then the reciprocal of the substrate concentrations that go with them. And then what you'll find, okay, is the slope is equal to Km over V max, okay? And that comes directly from the equation. Oh, come on. There we go, sorry. And then your y-intercept, all right? The y-axis is 1 over a velocity, right? So b is our y-intercept, so that is 1 over V max. And then your x-intercept, okay, turns out to be minus 1 over the Michaelis constant. But if you have, you can get your Michaelis constant by solving the slope for Km. So the V max, times the slope is equal to your Km, okay? So you can do Lineweaver-Burke analysis. So we could use Excel and plot 1 over V0 versus 1 over S, do a linear curve fit, use the equation for the line. However, our values are going to be very sensitive to any error in our measurement, okay? Because any change in the slope is really going to change what our values are that we get from our parameters. Because it's not complicated to do, we're going to actually fit directly to the Michaelis-Menten equation. And you're not going to have to figure out how to do this. I've posted a template Mathematica script for analyzing your data. You can, Campus has Mathematica license, so you can either install it on your computer or you can use one of the computer lab computers to do it. It takes not a long time once you've got the data to input. Okay, so we're going to use Mathematica to fit to the Michaelis-Menten equation, this equation right here, okay? And what the output is going to look like, all right? Well, we'll talk in lab about, how you do the input. But once you do the output, okay, this is what it is going to give you, okay? So the template I have for you is going to make a graph for you. I have 2 separate data sets that I graphed here. So I have, excuse me, sorry. I've got my reaction rate, my velocity, V0, versus substrate concentration. And so the points, okay, are the data points that I collected. And the line is how well the fitting fit to those data points, okay? Now this, I used artificially generated data, so all my points fall on the line perfectly and I get a perfect fit, but, so my correlation coefficient is like 1, but this is just for illustrative purposes. So the important thing to note is you're gonna have a line, okay, that tells you what, I have 2 data sets here, and so for my first data set, my Vmax was 3.99947, and this is going to be, the substrate concentration was in millimolar, okay, so this should be millimolar. I have to fix and so the units on, and this is millimolar per second, say, okay? So this is going to be a rate millimolar per second, and my Km is 1.99802 millimolar, okay? And then for the other conditions, it had the same, excuse me, it had the same Vmax essentially, 3.997, but the Km is higher, okay? So for curve number 2, my Vmax, I'm going to round both of these, so I'm going to say, 4.0 millimolar per second, and my Km is 5. Let's just again do it 6.0 millimolar. Okay, and I'm going to round these again just to make the numbers easier to talk about. So we've got 4.0, and this is 2.0 millimolar. All right, now the final thing we're going to talk about is we're going to talk about interpreting these curves, okay? And what are our kind of touch points on these curves, okay? So first of all, let's talk about Km, okay? So Km, I said, tells you something about affinity for substrate, okay? And if you recall, talking about myoglobin, okay? And we were looking at myoglobin binding to oxygen, right? And we had, again, a hyperbolic curve, right? And what we found with our curves for myoglobin and hemoglobin, right, is that whether they were shifted left or right told you something about affinity for the oxygen. Okay? Here, we're going to talk about affinity for the substrate, right? So, if we look, okay, for oxygen binding, we looked at the P50 value, right? So what I'm going to tell you is our Km value is analogous to the P50 value, okay? So Km is analogous to P50, okay? What it is it is the substrate concentration at which 1/2 of Vmax is observed, okay? So if P50 is the point at which half your sites are filled, okay, and Vmax is the point at which you have all your sites filled and then you release product, well then the halfway point to that is when you have half of your enzyme molecules saturated, right? All right, so how do we define where our Vmax is by just looking at this curve? In this case, the Vmax for both of them is 4. So we don't see it with the amount of data we collected, right? If we were to continue, these lines would go up and they wouldn't ever exactly reach 4. It's kind of the asymptote value, okay? It's where it's kind of the point that they're kind of just gonna touch on because it's an equilibrium and not a, I bind and that's it kind of thing. So the kind of Vmax is sort of the highest point that the curves go to eventually. Okay, again, you may not have collected enough data to measure Vmax directly. But the halfway point, okay, is going to be your Km, right? And since it has units of concentration, okay, again, the higher the concentration it took to get to the P50 value, the lower your affinity, right? Same thing here. So the more the curve is shifted right, the higher the Km value, the lower the affinity. All right? So more curve is shifted. So this point right here would be 1/2 of Vmax. That point right there. This is my Km right here. To the right. Higher Km value and lower affinity for substrate. All right, so those are all the things that you have to, or that I would like you to know and understand in terms of background before we actually go in the lab and do our kinetics experiments. As you do the experiments and then process your data, we're going to be getting a better understanding of, again, what these parameters mean, right? So each group is going to be not just measuring the kinetics under one set of conditions. You're going to kind of pick a situation to investigate that maybe would tell us something about the mechanism of the either of the enzyme itself or the mechanism of an inhibitor, and we'll talk more about inhibitors in class. Okay. So again, we talked about Lineweaver-Burke equations, just to to kind of emphasize what your data would look like if you have different experimental conditions. Remember that your Vmax is going to be dependent on the amount of enzyme that's there. Okay, so in a Lineweaver-Burke plot, that intercept is going to change. Whereas if I use more enzyme, okay, so let's say I'm going to use the enzyme that I had in blue, okay, and I'm going to double the amount of enzyme that I had there. I'm going to get a higher Vmax, right? The Km is going to be the same, right? My Vmax will go up. Okay, so it would, well, presumably be high. That was poorly drawn. So it's halfway point. So let's say I use more enzymes so that this is like 6. Okay, so my in that case, my Km isn't going to change. Okay, but my Vmax will change. So my Vmax is at 6. Okay, 3 is going to be the halfway point to that. So my curve is going to be halfway up at that point. Okay, so it's going to kind of look like that. Hard to draw on that like crowded plot, but all right. So hopefully, doing things in the experiment will help us, understand how this works a little bit more, and then we'll talk more in class about what we can learn from examining Km and Vmax, and we're going to talk about that catalytic rate constant. Okay, but I'd like to talk about enzyme mechanisms, okay, before we talk about catalytic rate constants, so that you have an idea of, here are all the little chemical steps that go into this enzyme catalyzing this reaction, so that you can wrap your head around what a fast K-cat is versus a slow K-cat. All right, Thanks for paying attention so long, and I will see you in lab.